question 285 in order successor in BST from LeetCode. Giving the root of a binary search tree and a node P in it, return the in-order successor of that node in the binary search tree. If the given node has no in-order successor in the tree, return null. So what is this question is asking us? It's asking us to return the in-order successor of a node P. So what is in-order successor? The successor of a node is the smallest key greater than p-value. So what does it mean? It says if the node p-value is 1, the in-order successor of 1 is going to be 2. Why 2, not 3? Because 2 is the smallest key which is bigger than 1. Number t between 1 and 3 we have 2. If we didn't have 2, 3 was the in-order successor. So let's try another example. Let's say if the p-value is 4, what is the in-order successor of 4? If we consider this binary search tree, the biggest number after 4 is 5, so we are going to return 5. So what if the p-value is 6? What is the in-order successor? Because there is no number bigger than 6 here, the in-order successor is going to be null. And as you see here, it has mentioned that if there is no in-order successor, we are going to return null. So one thing we need to know here is, like, we are talking about the binary search tree, and one of the properties of a binary search tree is the left node is smaller than root and right node is bigger than root. So we can use this property to traverse the tree and find the p node and find the successor, the in-order successor. Let's jump to the solution and the code and see how it works with an example. So for solving this problem, as I mentioned, we are going to use the binary search tree property, which is like the left node is bigger than root and root is smaller than right node. So for that purpose, we are going to traverse the tree starting from the root node until we find the p-value. And you might say, how can we know which one? Okay, we find p-value this way, but how about the successor? When we are iterating over, when we are traversing the binary search tree, we keep the successor, we keep track of the successor, and this is how we know, okay, what is the successor after finding the p-value. So if we go through an example, you can better understand the case. So first, we need to deal with special cases like when we don't have root or there is no p-value, which we are going to return none. So we are going to have a pointer, the current pointer, which is starting by pointing at the root value, and then we are going to have a p-value. For example, here, let's say the p-value is node 25, that we are going to find the successor of the node 25, right? So the while loop that is happening here, it's gonna compare the current node value with the p-value, and then decides it needs to go to the right side of that current node or the left side of that current node, and we keep updating the successor, and this way we keep track of the in-order successor. So let's start iterating over the iterating over the binary search tree. So as long as the current node is not null, we keep iterating over the nodes. So if the current value, which is 50 now, is smaller than 25, we are going to the right, and if it is bigger than p-value, we are going to the left, and we are updating the successor, because we know this is bigger than p-value and this might be the successor that we are looking for. So we put the 50 here as a successor because it might be the successor because it's bigger than 25 and it might be the successor. And we move the current pointer to the left side of this node because we know at the left side the value is smaller than the root, and we compare the value of the current node with 25 and see if it is smaller. If it is smaller, we are going to the right side, and if it is bigger, we are going to the left side. And this is bigger, and we update the successor because we know, okay, for sure between the p-value 25 and 50 there is another node which is bigger than 25 but is smaller than 50. So we are going to update this to 30, and we are going to move the current pointer to the left side of this node 30, and then we compare the 20 and 25. Is 20 is smaller than 25? Yet this is smaller than 25. So if it is smaller than 25, we don't need to update the successor because we are going to look for the smallest, bigger number for the p-value. So what we are going to do, we just need to go to the right side of this node because we are going to look for a bigger value or equal value to 25, and now we compare this 25 with 25. So this is the node that p-value that we are looking for, and we are going to return the successor, and the successor of this 25 is 30, and as you see 30 is biggest number, the actually smallest number that is bigger than 25. Okay, let's try another example to better understand this question and the solution. So let's say, let me clean here to avoid confusion. The current node is gonna start from root node again, and now this time we are going to have 80 as the p-value. So okay, 80 is the p-value that we have here, and we start iterating over the or traversing the tree. Okay, and now you start from the root node, which is 50. Is 50 smaller than or equal to 80? Yes, it is. So if it is smaller, we are not gonna update the successor and we leave it as it is, which is none. By default, the successor is none. Okay, so and then we just update the current pointer to the next right node because we are going to look for bigger numbers until we reach 80, right? And we check 60. Is it smaller or equal to 80? Yes, it is smaller and equal to 80. So we are not going to update the successor. We move the pointer to the right side of 60 because we know at the right side of 60 the number is bigger than 60. So we compare 70 with 80. If 70 bigger than 80, no, it is not. So we are going to move the current pointer to the right side of 70 because we know at the right side of 70 the number is bigger than 70, and there is a chance that number is bigger than 80 or equal to 80. So now if 80 is equal or smaller than 80, yes, 80 is equal to 80. So what we are going to do now, we update this and it's going to point to null, and we are going to return the successor, which is none. And as you see here, we don't have any node bigger than 80 in this binary search tree, and none is the right answer. The time complexity for this question, for this solution, is going to be linear because at the worst case we need to traverse like most of the tree, and the space complexity is 1 because we don't use any extra space. Thank you.